Good morning, everyone. I will give the presentation of our paper named The Real-Time Scheduling upon a Host-Centric Acceleration Architecture with Data Offloading. Nowadays, more and more safety-critical CPIs tend to be autonomous decision-making. It relies on artificial intelligence and machine learning components. These components are high data parallelism and computational intensive. To cope with the increasing computation requirements, the CPIs uses Host Accelerator Platform. The host means the general purpose CPU, which are used to deal with serial tasks, and the accelerator are used to deal with the parallel tasks. For example, the DSP Fabric GPU or FPGAs. In this paper, we take the GPU for example. To fully exploit accelerator's performance capabilities, we form the host accelerator platform as a two-stage model. At the first stage, the host offloads the code and data to the accelerators. And then the offloaded workloads are executed on the accelerators. In this paper, we aware two important factors. The first factor is the offloading time, the time spent by offloading the workload from the host to the accelerator. The second factor is the execution time, the time spent for executing the offloaded workload. The problem we want to solve is that there are many tasks that are sequentially offloaded and executed on GPU in parallel. How to find a proper offloading sequence and a good assignment strategy for the GPUs, ensuring that the overall duration is minimized. Here, the overall duration is also called the mixed span. In the following, we want to introduce the problem specification in more details. In our system model, we have a host and accelerator connected by a non-preemptive bus, and the accelerator contains M processors from P1 to Pm. We schedule n jobs tau 1 to tau n, and all of them are generated on the host. And then they sequentially offloaded to the accelerator. The offloaded jobs are executed in parallel on the accelerator. For each job tau I, we denote his offloading time xi, the time duration required to offload tau I from the host to the accelerator. And we also denote the work function wik, the total execution requirement of tau I when a then k processors. Moreover, we assume that the total workload is non-decrease. That means when a then more processors, the total workload may increase. The job's execution length is non-increase. It means that when a then more processors, the job will have a shorter execution length. We use cuff-I to denote the maximum parallelism degree of tau I. That means tau I cannot be assigned more than cuff-I processors. And for convenience, we use yi to denote the execution length if tau I execute at the maximum parallelism degree cuff-I. Moreover, we use the wi to denote the total workload if tau I is assigned exact cuff-I processors. We aim to efficiently schedule all jobs tau 1 to tau n on the host accelerator platform, such that the schedule's duration, which also called the mixed span, is minimized. Here, the mixed span is from the time that the first job starts his offloading to the time at which all jobs complete their execution. In the following, we discuss how to minimize the mixed span. Intuitively, we can schedule the jobs in a work-conserving strategy. It means that we can sequentially offload the jobs and execute them whenever there are idle processors. For example, we first offload the 3 jobs tau 1 to tau 3 one by one, and at time 1, when tau 1 completes his offloading, tau 1 can be executed as soon as possible because there are idle processors. And at T2, Tau2 complete his offloading. T2 can also be executed as soon as possible because there are also idle processors. But at T3, when Tau3 complete his offloading, Tau3 cannot be executed as soon as possible because all the processors at that time are busy. So Tau3 must wait for idle processors here. Unfortunately, under work-conserving strategy, jobs may be forced to execute it sequentially, which lead to very large mixspan. We will give an example to illustrate this. In this example, there are two jobs, Tau1 and Tau2. Tau1 has a unit offloading time, and his execution length is 2 when he reaches his maximum parallelism degree m-1. And Tau2 has a unit offloading time, and his execution length is L, which is much larger than 1, and his maximum parallelism degree is m. The work-conserving schedule is here. At time 1, Tau1 completes his offloading and is assigned m-1 processors. And at T2, Tau2 completes his offloading and there is only one idle processor. And according to work-conserving strategy, this one processor is assigned to Tau2, and accordingly, Tau2 has the execution length ml, and so the total mixspan is ml plus 2. We find that if we do not execute Tau2 at time 2, but instead we execute Tau2 at time 3 when there are sufficient number of idle processors, then the mixspan will be L plus 2, which is far less than the ml plus 2. This example inspires us that if there are not sufficient number of idle processors, a job should wait until there are more idle processors, then this job can be executed in a much less execution length. This strategy will significantly reduce the mixspan. So in the following, we will design the more smart algorithm based on this observation. Based on the observation, we designed the algorithm 1 to execute jobs. Only there are sufficient number of idle processors. In more details, we set a constant factor alpha and execute jobs only when there are alpha m or more idle processors. And moreover, we define the queue as a queue to store the sequence of jobs. Our algorithm executes jobs when there are enough idle processors. Here, enough means that the idle processor number is larger than alpha m. And look at this picture. In this direction, although there are idle processors, but we do not assign them to new jobs because these idle processors are too less to be assigned to unexecuted jobs. And in this direction, we can see that there are more than alpha m idle processors here, so there are enough idle processors to be assigned to unexecuted jobs. Look at line 4, we assign the idle processors to tau I like this. The first, if idle processors is less than the maximum parallelism degree cutoff I of tau I, then we assign tau I all idle processors. Just like this, the shape of tau I is changed to fit the number of idle processors. Otherwise, there are more than cutoff I idle processors, and in this case, we assign cutoff I processors to job tau I. For any assigned job, we first offload it on an accelerator and then execute it on his assigned processors. We now give some details about the implementation of algorithm 1. we let the job with the largest execution requirement be the last job in queue. Here, we use Wmax to denote the largest execution requirement among jobs. Moreover, we set the factor alpha to be the largest execution requirement divided by the total execution requirement among all jobs. Under this implementation, we can bound the mixed span as follows, where the W sigma is the total execution requirement, and the X sigma is the total offloading time, and Y max is the largest execution length among all jobs. M is the processor number. We now briefly introduce the proof of this theorem. Here, we first denote the tau k as the last completed job. In other words, the mixed span equal to the job tau k's finishing time, which denoted as Tf. And then we divide the mixed span duration into two parts, T1 and T2. T1 is from time 0 to the last complete job tau k starting time, denoted as Ta, and T2 is the duration during which the last completed job tau k is executed, and then the mixed span equals T1 plus T2. We first introduce how to bound the length of T1. Here, we note that T1 can be divided into two parts, To and Tu. To contains the time point at which the job offloads their workload, and Tu contains the rest time point. Tu equals T1 minus To. The length of To is the summation of the offloading time of tau 1 to tau k, and thus it can be bounded by the total offloading time X sigma. To bound the length of Tu, we find that, first, the total workload during Tu is at most W sigma, the total workload, minus the workload of tau k, Wk. And moreover, at each time point of Tu, we find that there are at least 1 minus alpha times m processors are busy. So Tu is bounded like this, which is the workload should be executed during the Tu divided by the minimum number of busy processors. And according to alpha's formula, we can find that Tu is eventually bounded by this formula, the W sigma divided by m, just like this. By now, we have bound the length of T1 as the X sigma and plus the W sigma divided by m, and in the next, we will bound the length of T2. We note that the execution of tau k has two possibilities. First, if tau k is executed on his maximum parallelism degree Kk. In this case, the length of T2 equals Yk, the execution length of tau k, and thus is certainly less than the Y max, which is the largest execution length among all jobs. And otherwise, the idle processors here is less than tau k's maximum parallelism degree, Kk, and in this case, tau k is then at least alpha m processors, and then the length of T2 is less than Wk divided by alpha m, and according to alpha's formula, tau 2 is bounded by W sigma divided by m, just like this. Thus, we have the upper bound of the length of T2 like this, and then this theorem follows. As we know that the optimal mixed span is larger than W sigma divided by m, and is larger than X sigma, and is larger than Y max. Therefore, from theorem 1, it is easy to see that the implementation one is 3-OPT. That means the mixed span solved by the implementation one is at most 3 times larger than the optimal one. We now to improve the algorithm 1 and obtain the totally different implementation. We call it implementation 1 star. Here at first, we set the alpha be the second largest execution requirement divided by the total execution requirement, W sigma. And then we let the job with the last execution requirement, W max, to be the first job in queue. Under implementation 1 star, the max span can be bounded by max fk. Here, fk is a function of k, just like this. The first item is the length of the offloading time of tau 1 to tau k, and the second item bounded the length of the no offloading time before tau k is executed, and the third item is the length of the duration during which tau k is executed. From theorem 2, we can derive that the max span of implementation 1 star is much smaller than implementation 1's max span. Moreover, we carefully design the weight of each job, just like this, and sort the jobs in a decreasing order of their weights. Then the maximum Fk achieves infimum. In the next, we design another algorithm called algorithm 2 from a new perspective. The main idea of this algorithm is to partition the jobs into 2 sites and schedule each site from a different strategy. In more details, we first light a new constant factor called a rule, and if a job with a cuff larger than or equal to rho m, then we call this job as a JE job. And otherwise, if a job with the cuff less than rho m, then we call it the LT job. For example, there are 5 jobs, and the jobs tau 3 and tau 4 have the same shape, so we only draw one job to represent both of them due to the space limitation. And here we set the rho m to be like this, and then from the partition strategy, we know that the tau 1 and tau 2 is a JE job, and tau 3 to tau 5 are LT jobs. After the partitioning, we then offload the jobs. We first offload the JE jobs by Johnson rule. That means we first offload the jobs whose offloading time is less than his execution length, and then we offload the jobs with the offloading time that is larger than his execution length. When the complete of JE jobs offloading, then we can offload LT job in an arbitrary order. In this picture, we note that we first offload tau 2 and then offload tau 1. That is because the offloading time of tau 2 is less than his execution length. And moreover, the offloading time of tau 1 is larger than his execution length. So due to the Johnson's rule, we must offload tau 2 at first, and then tau 1. After the offloading of these 2 tasks, these 2 jobs, we then can offload the LT jobs, tau 3 to tau 5. As the third step, we execute the jobs. First, we execute the JE jobs in a first in, first out way. That means at any time, we execute the job of JE who's finished his offloading earlier. And then we execute the jobs of LT in a first fade decreasing heat way. That means at any time, we execute the jobs tau I with a larger execution length and whose cuff fit idle processors. For example, in this picture, we first schedule tau 3 because he has the largest execution length, and then at time t we schedule the job tau 5 instead of tau 4. That's because although tau 4 have a larger execution length than tau 5, but at time t, top 4 cannot fit the idle processors, but the top 5 does. So in this time, we first schedule the top 5, and then when top 3 complete his execution, we can schedule the job top 4. By using the known result from Johnson and FFDH rules, the approximation ratio of algorithm 2 is derived as follows. So algorithm 2 has an approximate ratio 1 plus square root of 2 when rho equals square root of 2 minus 1. The proof of this theorem contains two parts. In the first part, according to Johnson rule, we can prove that the duration before the execution of LT jobs can be bounded by one OPT and data. Here the data is a positive number. And then the third part, the duration where the LT job execute can be bounded by a square of 2 OPT and a data. So the total approximation ratio is 1 plus a square root of 2. The next, we introduce our experimental work. In our experimental work, we randomly generate job sites with different job number and different processor number and different ratio between the offloading and the workload. And then we implement our algorithms. For example, the implementation 1 and 1 star and the implementation 2. And moreover, we also implement the baseline method, which have a ratio of 2.5 OPT. And this baseline algorithm first offload the jobs with 1 OPT and then executes them by Monas method with 1.5 OPT. We show the ratio between the mixed band solved by the algorithm and the lower bound, and we find that all our methods performs the baseline method, and the implementation 1 star and the implementation 2 outperform the implementation 1 here. We now give the conclusion. In this paper, we study the two-stage scheduling problem, which is in the first stage, jobs are sequentially offloaded, and meanwhile, in the second stage, the offloaded jobs are executed in parallel. We propose several algorithms to minimize the mixed bind. The first, we propose the implementation 1, which only needs to know very little information about the job site, and his approximation ratio is 3 OPT. It performs the baseline method. Moreover, the implementation 1 star and the implementation 2 need to know the parameter of each job in the job site. The implementation 1 star also have the 3 OPT approximation ratio, but it sorts the jobs in the job site and can get a better mixed band bound. The algorithm 2 have a better approximation ratio, just like this, 1 plus the square root of 2. And both of the implementation 1 star and the implementation 2 can outperform the implementation 1. Okay, that's all. Thanks.